Hello viewers, in today's session we are going to discuss the concept of differentiation under the integral sign, right? And we have already discussed the concept of differentiating an integral under the integral sign in our earlier videos. But here our prime objective is to see or to learn the concept of differentiating an integral under the integral sign with the help of this problem, right? So here we'll not only discuss the concept of differentiating an integral under the integral sign, but also will evaluate this integral, right? So let us start. So now here we have to evaluate this integral, that is 0 to infinity, and our integrand is 1 over x square plus a square raised to 4, right? So in order to evaluate this integral, let us start with this known integral, that is 0 to infinity, and we have a dx over say x square plus a square, and the value of this integral is given by pi over 2a, right? So we'll start with this expression. So here we have the power 1, and here we have the power 4, that is the exponent is 1 here, and here we have the exponent 4. So with the help of the concept of differentiating an integral under the integral sign, we'll try to get this exponent as a 4 by successively differentiating both sides, right? And let us first quickly see how we have got this expression. Now see, we know that this integral, that is integral dx over x square plus a square, this is a standard result, and we have here 1 over a tan inverse x over a. So the indefinite integral of 1 over x square plus a square is given by 1 over a tan inverse x over a. So now if we wish to find out this integral, that is 0 to infinity, then we have to make use of the limits, right? So first we'll take here infinity. So we have here 1 over a, then we have a tan inverse infinity over a is simply infinity, and then we have here x is equal to 0, that is simply tan inverse 0, right? So what we have done here, we have the limits from 0 to infinity. First we have taken x tending to infinity, so here we have tan inverse infinity over a, that is simply infinity, and we have taken 1 over a outside this expression, and then we have here x is equal to 0, so that we have tan inverse 0 over a, that is equal to 0, right? So we have 1 over a, and we know that tan inverse infinity is pi over 2, and tan inverse 0 is 0. So here we have pi over 2 times a, right? So this is an important result in integrals, right? And we can use this integral or this expression to derive other integrals also, right? So we'll now start with this integral or this expression to get the value of this integral. So now let us differentiate both sides with respect to a. So here we'll write del over del a, and here we have 0 to infinity, and we have dx over x square plus a square, and here we have del over del a and pi over 2a, right? So what we are doing here, we are taking the derivative of both sides partially with respect to a. So here we'll take a as a variable, right? So we'll differentiate both sides with respect to a. That's why we are here using the partial differentiation notation, right? So del over del a of this integral is equal to del over del a of pi over 2a. So now let us take this operator, that is the derivative, partial derivative operator inside the integral sign. So we have 0 to infinity, and we have here a del over del a, and here we have 1 over x square plus a square, and here we have a dx, and here pi over 2 is a constant, and we have del over del a, and here we have 1 over a. So here we are taking this a as a variable, and we are taking this x as a constant. So we are taking the partial derivative of both sides with respect to a. So now the value of this derivative can be obtained like this. We have del over del a of x square plus a square raised to minus 1. So taking x square plus a square to the numerator. So we have now here minus 1, then we have x square plus a square raised to minus 1. So here we'll apply the power rule for differentiation, that is n x n minus 1, and here by chain rule we have to now differentiate x square plus a square, right? So here we have minus, and here we can now write x square plus a square raised to 2, because here we have minus 2, and then the partial derivative of x square with respect to a is 0, and the derivative of a square with respect to a is 2a. So we have minus 2a divided by x square plus a square and whole square, right? And here the derivative of this expression 1 over a with respect to a is given by a raised to, here we have a raised to minus 1, that is simply minus 1 over a square. So now we have this expression 0 to infinity, and for this derivative we have here minus 2a, and then we have x square plus a square whole square. Here we have dx, and here we have pi over 2, and here we have minus 1 over a square, right? So now we have this integral, and when we consider this integral, then x is our variable. So we can take minus 2a outside the integral. So here we have simply 1, and here we have minus 2a, right? So now taking this minus 2a to this side, so we have now here 1 over minus 2a. So now we can simplify this expression. So we have here pi, here we have minus and minus get cancelled. So we have 2 times 2, 4. So this is now equal to 4 over a cube, right? So now we have this expression, that is integral 0 to infinity 1 over x square plus a square whole square dx is equal to pi over 4a cube. And we can conclude that when we have differentiated both sides with respect to a, then here the exponent, that is 1, is increased by 1. That is, here we have now the exponent as 2, right? So now let us again differentiate both sides with respect to a, and again we'll follow the same steps. So we have del over del a of this integral, that is 0 to infinity 1 over x square plus a square whole square dx. And here we have pi over 4 is a constant, and we have del over del a of 1 over a cube, right? So again I will take this partial derivative operator inside the integral sign, and will differentiate 1 over x square plus a square whole square with respect to a, treating x as a constant, right? So now we have this expression. So we can now write here 0 to infinity, and following the same steps here, the derivative of x square plus a square raised to minus 2 is given by minus 2 and x square plus a square raised to minus 2 minus 1, and then the partial derivative of x square plus a square with respect to a is 0 plus 2a, because the partial derivative of x square with respect to a is 0. So here we have simply 2a, here we have dx, and here we have pi over 4, and here the derivative of a raised to minus 3 with respect to a is minus 3, and here we have minus 3 minus 1, that is minus 4. So we can now simplify it, and we have here a minus 2 times 2a is minus 4a, and now we have the integral here. So we can now again treat x as a variable and a as a constant, so that we can take minus 4a outside the integral. So here we have minus 4a, then we have 0 to infinity, and we have dx over x square plus a square raised to 3. And here we have a pi over that is minus, here we can write minus 3 pi over 4, and here we have a raised to 4, right? So now we can take minus 4 to this side, so we can now write here 1 upon minus 4a. So this is 1 over minus 4a. So this is now a minus and minus get cancelled, and we have 3 pi over 16, and a raised to 4 plus 1, that is 5, right? So now we have the value of the integral, that is 0 to infinity dx over x square plus a square raised to 3 as 3 pi over 16 times a raised to 5, right? And now we have seen that when we have differentiated both sides, then the exponent is increased by 2, right? So when we have differentiated 2 times this expression, right, so the exponent is increased by 2. So here we have 1 plus 2, that is equal to 3, and here we need 4, right? So the exponent is to be 4. So we have to differentiate both sides again with respect to a. So now again differentiating both sides partially with respect to a, we have this expression, and then taking this partial derivative operator inside the integral sign, we have this expression, right? So taking x square plus a square raised to 3 to the numerator, we have here a negative 3, and 3 pi by 16 is a constant, and here we have a raised to minus 5. So we have now a 0 to infinity, and here following the same steps, here the partial derivative of x square plus a square raised to minus 3 with respect to a is given by minus 3, and then we have x square plus a square raised to minus 3 minus 1, and the by chain rule, the derivative of x square plus a square with respect to a is simply a 2a, and here we have dx, here we have 3 pi by 16, and here we have minus 5 a raised to minus 5 minus 1. So we can now simplify it. So we have 0 to infinity, And again we have the integral here, so we can again resort to this x as a variable here, and taking a as a constant, so we can take a minus 6a outside the integral, and here we have dx over x square plus a square raised to minus 3 minus 1 is minus 4, and here we have now 4, right? And here we have minus 15 pi over 16, and here we have a raised to 6, because minus 5 minus 1 is minus 6, and taking minus a raised to minus 6 to the denominator, we have here positive 6. Now taking minus 6a to this side, we have now here a 1 over minus 6a, and simplifying it, here minus and minus get cancelled. This is 3 times 5, this is 3 times 2, so we have now 5 pi over 16 times 2 is 32, and here we have 1, so 6 plus 1 is 7, so here we have a raised to 7, right? So viewers, the value of this integral is now equal to 5 pi over 32 times a raised to 7. So viewers, this is how, by the concept of differentiating an integral under the integral sign, we can arrive at these results, right? And the value of this integral is given by this expression. So here we can also deduce some important results. Now see, if we take, say, a is equal to 1, then we can here have a special case, that is the value of the integral 0 to infinity dx over x square plus 1 raised to 4. So taking a is equal to 1 as a special case, a square is 1 square, that is 1. So the value of this integral it can directly be obtained by substituting a is equal to 1 over here. So we have 5 pi over 32 times 1 raised to 7. So this is 5 pi over 32. So similarly, we can derive other results also by assigning different valid values to A.